Now let's start some example related to the bivariate distribution. These example covers the topics joint function of a two variable, marginal function of two variable, distribution function, expectation, covariance, and correlation coefficient. Now take an example: the joint probability distribution of two random variable x and y for a given table 1. Here the table 1 represent the x contain three values -1, 0, 1, and y contain the three values 0, 1, 2. Here these are the joint probability, where A represent the joint probability of when x is -1 and y is 0. This 2A means the joint probability of when x is 0 and y is 1. Now we have to find marginal distribution of x and y and conditional distribution function of x given y is equal to 2. Now the solution of example 1, we have given table 1 in which we have given the joint probabilities of x and y. Here first we find the marginal probability. If we add a plus 2a plus a, we get 4a. If we add 3a plus 2a plus a, we get 6a. And we add 2a plus a plus 2a, which is 5a. These represent the marginal of y, means marginal function of y. Similarly, if we add all this 6a, if we add corresponding to 0, we get 5a. If we add corresponding to 5, we get 4a. These are the marginal probability of x. Now here we show the marginal distribution of x from a given table, means the marginal probability of when x is -1, we get 6a. When marginal probability when x is 0, we get 5a. And when probability x equal to 1, we get 4a. Similarly, we find the marginal probability or marginal distribution of y. When probability y equal to 0, we get 4a. Y equal to 1, we get 6a. And probability y equal to 2, we get 5a. Now the second part of the example 1, we have to find the conditional distribution of x given y equal to 2. Here we have to find the probability when x equal to x given that y equal to 2 is equal to the joint probability when x equal to x intersection y equal to 2 divided by probability of y equal to 2. Here we note this is a marginal probability and this is a joint probability. Now we take x equal to -1, so we get probability x equal to -1 intersection y equal to 2 divided by probability y equal to 2, which we find by the help of previous table. We get 2a, and probability y equal to 2, which is marginal probability, we get 5a divided by, we get 2 by 5. Similarly, if we take x equal to 0 and x equal to -1, so we find the remaining conditional probability when x equal x vary given that y is 2. Now taking another example, the joint probability distribution of two random variable of x and y for a given table 2. Here in the table 2, we have given the joint probabilities of x and y, and we have to find the probability when x is less than 1, y equal to 2, probability x is less than 1. Third, when probability y equal to 3, probability y is less than equal to 3, and probability x is less than 3, y is less than 2. Now we discuss the solution of the problem number 2. Here in the given problem, we have given the joint probability distribution table in which we have given the joint probabilities of x and y. Now if we add all corresponding x equal to 0, we get 8 by 32. Similarly, corresponding to x equal to 1, the complete row, we get 10 by 16, and similarly 8 by 64. These are the marginal function of x. And similarly, if we add the columns, so we get the marginal of y. Here, the first part, we have to find the probability x is less than equal to 1 and y equal to 2. It means x is less than equal to 1. It means when probability x equal to 0, comma y equal to 2, plus probability x equal to 1, y equal to 2. So the joint probability when x equal to 0 and y equal to 2, x equal to 0 and y is equal to 2 is 0. And the probability when x equal to 1 and y equal to 2, it means when x equal to 1 and y equal to 2 is 1 by 16. So similarly, in the second part, we have to find the probability x is less than equal to 1. So we add the probability x equal to 0 and plus probability x is equal to 1, which is, these are the marginal probability of x. So we add the probability corresponding to 0, which is 8 by 32, and corresponding to 1, which is 10 by 16. So we get 7 by 10. In a similar manner, if we find the probability x equal to y equal to 3, so we write the marginal probability when x y equal to 3. The fourth part, we have to find the probability y is less than equal to 3. It means we add all the marginal probability y equal to 1 plus y equal to 2 plus y equal to 3. So we get 20 by 64. These are the marginal probability. Similarly, if we have to find the probability x is less than 3, y is less than equal to 4. So here there are so many combination. Means first we vary x is less than 3. It means it's take the value x equal to 0, x plus x equal to 1, x equal to 2. When y is less than 4, y is less than 4 and y is less than 4. So again, that probability x equal to 0, comma y is less than 4, it take the 4, y take the 4 values. 1 when x is 0, y is 1. Probability x is 0, y is 2. Similarly, probability x is equal to 0, y is equal to 3, and so on. Similarly, for the second one, the joint probability when x equal to 1, y is 0, x equal to 1, y is 2, and so on. If we add all this probability, we get 9 by 16. Now the third example, two tetrahedron with sides numbered 1 to 4 are tossed. Let x denotes the number of downturn phase of the first tetrahedron and y is a downturn number greater than equal to x. So we have to find the joint density function of x and y, marginal density function of x and y, probability when x is less than 2 and less than 3, the conditional distribution of y given x equal to 2 and 3, expectation y upon x equal to 2 and expectation y upon x equal to 3, correlation coefficient. So the solution of the previous example, we have to given x denote the number of downturn phase of the first tetrahedron and y is a downturn number greater than equal to x. Therefore, the random variable x comma y takes the value 1 1 1 2 1 3 1 4 2 1 2 2 2 3 3 4 and 4 4, because x is always less than y. The condition is given in the example. So the table of joint distribution function is x take the value 1 2 3 4, y take the value 1 2 3 4, because x and y are the faces of the tetrahedron. So when x is equal to 1 and y equal to 1, so the joint probability is what? Is 1 by 16, because total we have 16 cases. So the joint probability of when x equal to 1, y equal to 2 is again 1 by 16. When x equal to 2 and y equal to 2, we have 2 by 16. And similarly, we form that joint distribution table. Again, if we add corresponding to y, we get 1 by 16. Corresponding y equal to 2, we get 3 by 16. And similarly, if we add the column x equal to 1, 1 by 16 plus 1 by 16, 1 by 16, we get 4 by 16. So these are the marginal function of x and these are the marginal function of y. Here the sum of this is always 1. So in the previous table we find the marginal distribution of x and marginal distribution of y. These are the marginal distribution of x and these are the marginal distribution of y. Okay, now the third problem, we have to find the probability when x is less than equal to 2 and y is less than equal to 3. So we take first x is equal to 1, y equal to 1, x equal to 1, y equal to 2, x equal to 1, y equal to 3, plus now x equal to 2, y equal to 2, x equal to 2, y equal to 3, because x is always less than y. This condition should be remembered, and by adding this probability we get 3 by 8. Similarly, we find the conditional distribution of y given x equal to 2. So probability of y equal to y given that x is equal to 2 is probability of y equal to y intersection x equal to 2 divided by probability of x equal to 2. So let's change the value of y. We get probability of y equal to 2 given that x equal to 2. So the probability of y is equal to 2 intersection x equal to 2 divided by x equal to 2. The value of y equal to probability y equal to 2, x equal to 2 is from table is 2 by 16. And the marginal probability x equal to 2 is 4 by 16. We get 1 by 2. In a similar manner, we can find the probability of y equal to 3 given that x equal to 2 and probability y equal to 4 given that x equal to 2. And in the similar manner, we can find the conditional probability of y given x equal to 3. Now we find the expectation of y given x equal to 2. So the formula of expectation is summation yj into probability y equal to yj given that x equal to x2. Now where j varies 1 to 4, so we write 2, that is y2, because y1 corresponding to y1. When we find the probability y equal to y1 x equal to 2 is 0, that's why we start 2 into probability y is equal to 2 given that x equal to 2 plus 3 into probability y equal to 3 given that x equal to 2 plus 4 into probability y equal to 4 given that x equal to 2, and this can be found by the conditional probability which is previously defined. So the expectation of y given that x equal to 2, we get 11 by 4. Similarly, we find the expectation of y given that x equal to 3. So we take summation yj, probability y equal to yj given that x equal to 3. Now y1, y2, y3, y4, we find the conditional probability and we get 13 by 4. So similarly, we can find the correlation coefficient between x and y. So for the correlation coefficient, we have to find the expectation of x, expectation of y, expectation of x square, expectation of x square, y square, and expectation of x and y. So the expectation of x is x fx. So 1 into 4, 1 into 4 by 16, 2 into 4 by 16, 3 into 4 by 16, 4 into 4 by 16. We add all them, we get 5 by 2. Similarly, we can find the expectation of y. So 1 into 1 by 16, 2 into 3 by 16, 3 into 5 by 16, 4 into 7 by 16. We get expectation of y. And similarly, expectation of x square. So we take a summation x square fx, 1 square into 4 by 16, 2 square 4 by 16, and similarly we get 15 by 2. Now when we find the expectation of x y, so we take summation x into y, joint function of x y, that this is the joint probabilities. So we write x into y, 1 into 1 by 16, 1 into 1 by 16, 2 into 1 by 16, and 3 into 1 by 16, plus 4 into 1 by 16, plus 4 into 2 by 16, 6 into 1 by 16, and 8 into 1 by 16. In a similar manner, you find the expectation of xy, which is 135 by 6. Now the variance is what? Variance is the expectation of x square minus expectation of x ka whole square. So we get 5 by 14.